Okay, let's start. So last time we were concerned with dealing with fractional derivatives. The background is that in general we will not get an L2 estimate for the time derivative. So as we will see, we will only get something weaker, at least in the general case. And therefore we introduced the notion of a fractional derivative by means of the Fourier transform, and have seen two things. First of all, we have seen or basically one thing which kept us busy. We have now a new, more refined compactness result, which only I refer it again. Because this is what we will need. That is what we have shown last time. That was the theorem 24.2, which dealt, I make it short. So what we had is, we had here, as usual, so to speak, concerning the space regularity, the L2V, V being the small space, let's say the H10 space. In time, we only had H gamma 0, 0T V star, V0, where the Galerkin triple was like that. V embedded into X continuously and compact. X embedded continuously into V0. So V0 could be a larger space or not. And then what we have seen is there is a continuous embedding into now LP 0, L2 0Tx, the middle space. The middle space will be typically the L2 omega space. And the important thing is this embedding is compact. That means if we have boundedness in these two spaces, we not only have reconvergence, which is good for linear terms in the equations, but not sufficient for nonlinear terms, but we also have strong convergence then in this L2 space. And this will help us and will be enough to go to the limit, what we finally want to do. Okay, now the question is how to get this information about the H gamma. And I give one theorem. Maybe I don't prove it because we will not use it directly. And because then in our proof we will prove really this result directly by really looking at the Fourier transform and giving an a priori estimate for the corresponding term in the form of the Fourier transform. So how to show that a function has this fractional derivative in time? And this is the next proposition. As I said, I'm not going to prove that. The next proposition, which basically again starts with a Galerkin triple. Now the spaces are denoted by H and V prime. So now we're requiring a little bit more because we require that we have Hilbert spaces. And we require really, so to speak, everything what is related to a Galerkin triple. So we have here not only continuous but compact embeddings here and here. And we have in addition what we called the consistent dual space structure, which basically means that the duality pairing between V and V prime, so that V prime is really the dual space of V, and that the duality pairing is really an extension of the scalar product of the middle space H. So that is really, so to speak, the full program with respect of the Gelfand triple. And in this situation, we can show the following. Let me first write it down, and then we I indicate what this new space means. So if we have an alpha between 0 and 1 over 4, then the embedding L2 0 TV, so that is what we typically have from the typical energy estimate with a solution. And assume that we now, concerning the time derivative, we know the following. We have a time derivative with values in V prime, so that is the typical thing. But we do not require that this time derivative is an L2 function, but we require that's only an L1 function in time. So again, so what is this? So these are, this W11 are those functions which are L1 functions, and the time derivative, the weak time derivative is an L1 function, and the 0 means that at the boundary of the time interval, so at those 2 points, the function vanishes in the trace sense. So if we want to apply this, this is a bit of a technical problem, because typically we will not have this. Here we will have an initial data, and here we will have no requirement at the final time. So to apply this theorem, technically we have to expand a little bit the time interval, prolongate the function by, for example, constant prolongation, but of course the zero prolongation, which has problems, as we will see in a second, so it's not so 100%. The technicalities are a little bit given. So, but anyhow, if we have this L1 estimate of the time derivative, then we have a continuous embedding into such an fractional derivative space with values in H. So then we could use this corresponding compact embedding theorem above. So these are now the technical preparations, and now we would like to start with the existence and uniqueness proof. For the time-dependent Navier-Stokes. It's always incompressible, I don't mention that. Okay, before we start, maybe to put the whole thing a little bit into perspective. Of course, all these things have to do with the notion of solution. I said already, maybe that sound a little bit ridiculous, but I think it brings the things to a point. All the existence business, we could make our life very, very easy, for example, by saying every function is a solution. Why not? Of course, it's not a good notion of solution, because certainly we don't have uniqueness then. But that indicates, of course, the larger the space is we are looking for a solution, of course, in principle, the easier it is to find a solution. The smaller the space, the harder it is to find it. Therefore, we have, and it may not exist, therefore we have weak solutions in situations where we don't have classical solutions. On the other hand, another thing we would like to fulfill is uniqueness of the solution, because that only shows that the model, so to speak, is a complete description of the situation. And the weaker the solution is, of course, the harder it will be to show uniqueness. So these two things are interconnected by the possible regularity. The more regularity we can show already incorporated in the notion of solution, or then in a second step, the easier it will become to show uniqueness. and the other way around. And now, maybe I should have told this before, but then maybe you would have said, okay, why don't we stick to 2 dimensions? In 2 dimensions, the situation is, not very surprisingly, much easier than in 3 dimensions. In 2 dimensions, we will later on see that we can show more regularity. In 2 dimensions, we will get an L2 estimate for the time derivative. So we can, in principle, we could forget about all these things in 2 dimensions, not in 3 dimensions. So in 2 dimensions, we could have made a much more simpler proof. Okay, but we also wanted to have it, of course, also in 3 dimensions. In 3 dimensions, we need this machinery. But concerning the uniqueness proof, later on, we will only be able to give a proof in 2 dimensions, a uniqueness proof for the weak solutions, by this increased regularity. This is not so very much surprising that we cannot do more, because the other part, the uniqueness for the global 3-dimensional weak solutions, which we will finally have shown to exist, this is the millennium problem, or this is one of the millennium problems. So if you can show the uniqueness, you can earn $1 million. Of course, it's also not so much, but would be okay. So that would be something to look at. So the program now is we show existence. We show first existence for what we can do, and this is n less or equal to 4, so including the important cases. And then we show uniqueness by increased regularity for n equals to 2. So let me write down the problem. So what do we have? We have a space V, a subspace of H10, omega Rn. And we have a space H, subspace of L2, omega Rn, and both are divergence free. The first one just by definition, and the second one as the closure of divergence-free functions. So by working in these spaces, we get the pressure-free formulation. So if we now look at the weak formulation in this space, testing with these divergence-free functions, the pressure term vanishes because the gradient of pressure times the test function. If we do partial integration, we get something up to the sine pressure times the divergence of the test function, so this term vanishes. So we get the pressure-free formulation, and I write this down we can write this down in the following form. Time derivative of v plus a of v. A is the linear operator related to the dissipative term, to the multidimensional minus Laplacian, so to speak. And then we have our nonlinear term, PVV. So this is the vector field V driving itself. This is always to be understood as operators on V prime. So these are all these are all quantities in V prime. So the B is a mapping from V cross V to V prime, and of course we have to have we check that this is well defined. Equals the right hand side F. So that's all in V prime, let's say. And then we have our initial data, which then, okay, we have given a sense to that. But that will be also typically in V prime. Okay. So now let me first state the existence theorem and then do the proof. What we can prove is the following. So, sorry, for some reasons, that there are under some conditions we can also do n equals to 4, but we will not do that. So we restrict to the two important cases, 2 and 3. So we have n less or equal to 3. We have not very much regularity on the domain required, just a bounded domain. We have those spaces as defined above. And we have a right-hand side, we have an interval, a finite interval, but not restricted in size. So what we are doing is a global in time global in time proof. So if we show an existence result for any given time interval, and therefore, of course, also for every time, without saying something about the asymptotic behavior in time. Another version of existence result would be to say there is some time interval such that there is a solution. That's also a typical kind of existence result for time-dependent problems. That's a much more weaker version, because then this time interval typically depends on the data. These things come in if, for example, we work with something like Banach's fixed point theorem, and we have to enforce the contractivity of the fixed point mapping, and then typically the length of the interval will be something which enters the contraction constant, the Lipschitz constant, and therefore we can only get existence results for small time intervals. That's also possible here under other conditions, but then the question comes up, can we prolongate the solutions? Can we go step by step? Is this small time interval actually independent of the data, because it only depends on some on some bounds, which we assume, or is this not possible? Might it be possible that there's a blow up in the solution, for example, in finite time? But this is not the case here. Here we go directly for a global in time existence proof. We have the right-hand side in the weak sense, so L2 0 TV prime. And U0 is a little bit more regular. It's not V prime, it's from H. So again, the typical spaces you see here again. What do they mean? And then the assertion is then there is a solution of the following regularity, L2 0 TV. So to speak, first derivatives in space, so to speak. L infinity, L infinity 0t h, and finally, and this will gives us then the possibility to use this final proposition we have not shown, and via this to use the compactness embedding W11 0t v prime of the Navier-Stokes equation. So, okay. The procedure is, as always, so to speak. So we do an approximation. Here again via Galerkin. Galerkin in space. So we discretize in space and keep the time. Then we have our approximate solutions. First of all, of course, we have to show that those approximate solutions exist. That is here not so complicated as in the stationary case, where we had to refer to Brouwer's fixed point theorem. Now we have a system of ordinary differential equations, as we have seen already several times. So what is the situation? We have spaces Vk, finite dimensional spaces. You might think them defined via finite elements. So abstractly they exist just because of these spaces are separable, and concretely you may think in terms of finite elements or in terms of spaces spanned by eigenfunctions. These spaces are supposed to be nested. So we always add one further degree of freedom. The K is the capital K is the dimension. The basis we denote by W1 to WK. Not sure we need an orthonormal basis, I don't think so. What we of course need is that we can approximate every element in V by a linear combination of those functions if we, as good as we want, if we choose the K large enough. Meaning that if we look at the union of all those VKs, they are dense. This set is dense in V, so the closure of this set is V. So, okay. That means a function Vk in time, which now does not take elements, images in V, but only in Vk, can be written as a linear combination of these basis functions. This is now here is a bit complicated with this, with a K, because there are small and large K, so all these Ks up till now were large, and now the running index is a small k, up to capital K. And now we need some notation for the coefficient. We call this function G. So, okay, it's a little bit overdone, I would say, but anyway. So in any case, it's a coefficient belonging to this K, this space with a capital K, with the index small k, and it's depending on time. So this is now a function, so to speak, going from 0t to Vk. And to determine this function is, of course, equivalent to determine those coefficient functions here. So these are now real valued functions we are looking for on the interval 0t. And the requirement for these functions is that we do a Galerkin approach. So we say those functions are supposed to fulfill the Navier-Stokes equation, but only by testing with the same space. So in this sense, saying that the residual is not 0, but it's only orthogonal to this finite dimensional ansatz space. Exactly what we do in a Galerkin method. So it's a Galerkin method. So we have here time derivative of Vk times the test function, and of course we can restrict ourselves here to the basis functions. Then we have here the linear part. Then we have our nonlinear part, given here written with the operator capital B, given by this trilinear form small b, in the variables Vk, Vk, and the test function Wj, and finally the right-hand side Fvj. So the j's are running here up to capital K. So we have here capital K many equations for this capital K many functions. And then we have not only this ODE, we will see in a second that's an ODE, we will have initial data, the same thing, so we do here the same projection for the initial data. So this is an ODE, or a system, a nonlinear system of capital K ODEs. Why? If we now plug in for those functions k, k, g, k, k. Why is this? If we now plug in this representation of the solution, multiply everything out as far as we can do, as far as it's the linear terms are concerned. And the important thing is what we have to look at. And here we get something like, let's call it m times the time derivative of gk. And then we get here something like the mass. Now we need another letter. Let's call it, okay, let's call it A tilde. A tilde, gk, k. And then we get here a nonlinear term, whatever. Let's call it phi of gk. But where's the small, where's the big? Oops. I should have chosen other letters here. Equals the right-hand side. So what do we? So this is the mass matrix. So this is just the matrix of the scalar products of the basis functions. This is the stiffness matrix. And this is our nonlinear term. And in any case, what is important is, the only thing what we need here, this here is continuous in G. So that we have here a matrix in front of the time derivative, that's no problem, because this matrix is invertible. We can think of having everything multiplied through with the inverse of m, and would show up here and here, and then we would have the typical form, explicit form of a system of ODEs. So what about existence now? Okay. How can we argue? The problem is, of course, that here we will have not a global Lipschitz continuity property, so we cannot just use Picard-Lindelöf and get it in one step, the existence. What we could do is, as I indicated just before, we could go for a small time interval, apply Picard-Lindelöf, so looking for the contractivity property here, looking for a small time interval, and then see how to prolongate this. An alternative way would be to go for Peano's existence, the Peano theorem, which only needs the continuity of the right-hand side, and which only gives local existence. So this is sure that we have local existence. So we have a t whatever tilde less than t. And then the question is, do we have global existence? And for having global existence, we need corresponding behavior of the solution. So what should be avoided is that the solution somewhat explodes, that the solution reaches the time of the domain of its existence, the boundary of the domain of its existence. What we will later on prove by the a priori estimates, what we are going to do, they will in particular show the boundedness of the solution, a global boundedness. So that's the strongest thing not strongest, but that's of course in any case sufficient and then we have global existence. So in some sense, these proofs are a little bit intertwined. So first, we can only work on the small time interval, showing this. In the next step, what we are going to do, looking at the a priori estimates, showing, and by this showing the boundedness, this gives us the possibility to have the existence on the full time interval. Okay. So now we need a priori bounds. And we start with the energy estimates. So energy estimates is that means nothing but we test with the solution. So now we could argue, okay, how do we do that? We just have to look here. What we have to do here is, so this is, so to speak, here not yet an this formulation is not yet integrated in time. This is just pointwise in time, just a pointwise formulation of an ODE system in time. So technically, what we do is we multiply here with the corresponding coefficient, and so first of all we do partial integration here, then we multiply with the coefficient, and then we sum up. So we get, do I tell you now something, a nonsense? Wait a second. That was nonsense. We would like to have here, so, okay, again. So we multiply here with the corresponding jth coefficient, and then sum up, and then we get here the Vk in, and correspondingly here and here. Because the whole thing here is this trilinear form is a nonlinear mapping, because it's product times term times term times term. One is the derivative, but in each of the components, of course, it's linear for having the others fixed. So what we can do is now, and I don't write this up, so what do we get then? Then we get here something which has the form time derivative of Vk times Vk, so this is 1/2 time derivative of Vk squared. So we can integrate this out in time after we have integrated the whole thing here in time. So we get the corresponding squared term at the final end of the time interval. Let's say we don't go over the full interval as 0 to capital T, but only to over a fraction 0 to small t. Then we get it at small t minus the initial term. And here we get something like the energy norm, which is equivalent by Poincaré to the H10 norm. So here we get in space the H10 norm integrated in time. So here we get something integrated in time. Here we get something pointwise in time. Yeah, and this term, it vanishes. This we have studied already for the stationary equations. That's a good thing, that this going for the energy estimates, the nonlinear part doesn't play a role at all, and yeah, this term just is then something which we can separate and so on. So what we get, let me write it as in the linear case or stationary case. We have done this already twice. We get now the following estimates. We have here, let me write it explicitly, we have the Vk in time. The, why do we square it here? Okay, it doesn't matter. The L2 norm in space, pointwise in time, so the supremum over the time interval. because here we had this derivative, which time integral over the derivatives gives the upper value minus the lower value. And then from the second term, we get the time integral of the Vk now in the V space. So in the H1 space, in the H1 subspace, doesn't matter whether S or. So these are bounded by the data. So these are the two a priori bounds that we have, and that's exactly the a priori bounds we always have. We already had for the heat equation. So this comes from the dissipative term. The convective term does not play a role. This comes from the time derivative. That's the old story, nothing new. But of course, it's now not enough to go on. Now, the next thing is estimate for the time derivative, the harder part. Okay. And here we argue like the following. So we have our function Vk, which is defined on an interval, on the interval 0t, and takes values in V, actually in the finite dimensional space. Okay. We prolongate that because we would like to do Fourier transform, so we have to have it defined on whole R. So we prolongate it to something what we call Vk tilde, which is now a function from R to V. How we can do that? Not sure whether we can avoid it here, because maybe we could even prolongate it continuously in this specific case. So, but we don't do this, and we prolongate it just trivially by 0. So we just define this function to be 0 outside of the interval. But this has now a consequence. Now this function becomes discontinuous in time. So now if we would look at derivatives, at any kind of distributional derivatives, we get contributions from these jumps. We get 2 Dirac distributions into the distributional derivative. Just wondering whether we could avoid this, but I'm not 100% sure. So in general, of course, we would not be able to avoid this because that is not a smooth function, but here it is. But anyway, we do it in this way. Okay, so consequence is, let's call it like that, has Dirac distributions. Okay. Now, similar to what we did before, we now, so this is the time derivative. So we look, so to speak, at the term which is supposed to be the time derivative. We look at the term Vk, which is f, and now we subtract everything a part of the time derivative. So a Vk minus b Vk. So this is now a function from 0t to v prime, and we do the same thing. We also prolongate and we get something which we call fk tilde. Now the equation what we have, this equation here, in the distributional sense means the following. if we now look at the time derivative, not at the time derivative of Vk, but we have here the prolongated function tested, and we look at the time derivative. So what will that be? That will be just the weak derivative, so to speak, on the interval 0t. Outside we get 0 because of this constant prolongation. But then at the 2 points from negative to 0 and from capital T to bigger than t, we have jumps, so we get Dirac distributions. The first level we have, so to speak, jump up. We get plus a Dirac distribution, then we jump down, we get a negative Dirac distribution. So what we get here the usual, so we get the time derivative in. This term is identical with the fk. And here we can prolongate because there are no derivatives involved. And now our Dirac distributions are V0, Wj, delta 0. So this is the Dirac distribution at t equal to 0, minus Vk at capital T, Wj times the Dirac distribution at capital T. Okay, so this is the j always runs to capital K. So now we do the Fourier transform of this equation. What does that mean? Here in the first part, we discussed this already. Why is it reasonable to look for Fourier what gives us the basis to define fractional derivatives in terms of Fourier transforms? The reason is if we go to Fourier transforms, derivatives becomes to algebraic actions, to multiplication with a certain term. And what we just did, we did not take this term to the power 1, but we only took it to a fraction. That was our definition of the fractional derivative. So if we now do here the Fourier transform, then we get, okay, the first term, we get this factor. The factor is 2 pi I tau. Tau is now the transformed variable, so to speak, the frequency variable. Then we get here the Fourier transform of the Vk tilde. And because of linearity, we can write it, it goes through the scalar product. So that is the time derivative after transformation. So in the other part, it's the same thing. It's the Fourier transform of fk. And then we still have the Fourier transforms of the Dirac distribution. And here we get now the Fourier transform of the delta at 0 is just a factor, is just 2 pi to the minus 1/2. And in the other, for the delta t, we get the same factor times e to the minus 2 pi I t times tau. So actually this is times, of course, what we have here, the Vkt Vj. So this is the general formula, which if we apply it to an evaluation point equal to 0, then this becomes a 1, and then it reduces to this here. Okay, so up till now, this is an identity only dealing with the basis functions. But of course, from the basis functions, we can, in a first step, come to every linear combination of the basis functions. So we can come to the full spaces, to the full space Vk. And let's see how we proceed. Okay, we can here come to the full space vk, so what we have to do is we have again multiply with these g coefficients and sum up. So instead of the wj's as a test functions, we can also use the fk as a test function. Sorry. We don't want to have the fk, the vk. We want to have, let me write it down, what we would like to have. We would like to have as a test function, because we want to have here the same function as here again, we would like to have as a test function the function Fourier transform of the prolongated solution in tau. How do we get this? We multiply, so where is it? If we take the Fourier transform by linearity, it means to go with the Fourier transforms on the coefficients or the prolongated coefficients. So we have to take the Fourier transform of the prolongated coefficients, multiply here in the equations and sum up. Let's give this equation a number. So this is this right? Which one is this? It has no number. Okay, let's call it star. So with the Fourier transform of the coefficient function and then summing. So what do we get? Here we get then the L2 norm squared up to this factor. We get the L2 norm, so we have this factor 2 pi I tau, so time, so this is something like a time derivative. If we think back in the non-transformed version, this is something like a time derivative. But it's now easier to handle because everything is algebraic now. That's the whole business here. So we have here something like the Fourier transform of the vk tilde at tau in the scalar product squared, so in the h norms, in the scalar products on the h norm squared. And on the other side, we have here the Fourier transform of the fk tilde at tau times the Fourier transform. Is this correct? Yeah. Yeah, that's okay. Everything is hidden in the fk. Fourier transform of the vk tilde. And then the terms which came from the Dirac parts. So 2 pi minus 1 v0 Fourier transform of vk tilde at tau. And finally minus, okay, let's write it in this form, vk at t, and then the Fourier transform of the same thing. And here we still have a factor times e to the minus 2 pi I tau t. Okay, so what is the procedure? What we'd like to get is, we would like to get a bound on this term here. Maybe not on the full term, because that would be the time derivative, but maybe only on a fractional power here of the tau, so we have to get estimates of the right-hand side. Let's see what we can do with the right-hand side. Na, wo geht's denn jetzt hier weiter? Hier. Okay, so 90, wo ist die richtige Seite? Okay, I claim the following, that we can do the following. So this is the important term here. So let's start with this term. So this term, of course, we can estimate here via let's first look, without the Fourier transform, look at this term here. Fk tilde t in the V prime norm. So this is now the non-transformed situation, and we integrate over whole R. We have here the prolongated situation. So what can we do? Where is the definition of this is above? So the first part is trivial. It's just the right-hand side, and it only lives on 0t. So everything only lives on 0t. So we are back here to the interval 0t. So this is obvious, this first part. The second part is just the continuity of this operator A representing the vectorial Laplacian being a continuous mapping from V to V prime. So we just can estimate this by, actually a constant times the norm, and if we take here the norm, what we here do implicitly, which is not necessary, otherwise a constant would come in. If we take here the energy norm, so this is just the norm defined by this vectorial Laplacian, then it's even an identity. It's even without a constant. Otherwise, if we would think here of an H1 norm, we would get a constant here. So it doesn't matter. So, and finally, and that we have checked, this nonlinear part is also a continuous mapping from V cross V to V prime. So we can also estimate here correspondingly, that's now a bilinear mapping, so boundedness of a bilinear map, so continuity means boundedness, and boundedness means constant times the norm of the one argument by the norm of the other argument. So these are the same here. So we get here a square, and we get here V. Okay, so. And what do we know about this? Here we have our a priori estimate, even in the L2 setting. And here we also have our, so we have an a priori estimate on this one. Should write here also T. And therefore, we also have an a priori estimate here. So we are in a fixed time interval, so the L1 is weaker. So we have to be a little bit, concerning this relationship between L1 and L2, we have to be a little bit careful. If we work on a bounded domain, which in space, of course, we always do, and in time, usually we also do, we have the ordering of the LP spaces. So L1 is larger than L2. If we have an L2 estimate, we have an L1 estimate. In more general. We have to be careful if we go to whole R. Then this relation does not hold anymore. So in the transform setting, or dealing with a Fourier transform, we have to distinguish whether a function is in L1 or in L2. And there's not such a clear relationship between these things then. But here it's clear, so the whole thing is bounded. So what we have here an a priori estimate on this term, so on the basic term here, but unfortunately only in, well, let me write it in this form. So what we have an a priori estimate for this F tilde in L1 0t, not L2 0t, unfortunately V prime. That's where the whole problem comes from. If we would here already in L2, yeah, no problem. Okay. So now, if we transfer this now, so L1 is actually stronger, in some sense stronger than L2 on whole R. So that means now having an L1 function here, having a bound in the L1 norm, that means for the Fourier transform, we get an L infinity bound. Just look at the definition of the Fourier transform. If you can take the f term, so to speak, out of the if you the rest, so to speak, the convolution kernel is something bounded. It's bounded by 1. So this can be bounded by 1, and then if this is allowed, if you have an L1 function, then only the L1 integral is remaining. So you get, for the Fourier transform, for every tau, you get then a bound. So you get an L infinity bound on the Fourier level. So the consequence of this is, as I said, the L infinity bound on the Fourier level of the Fourier transform of the fk tilde tau. So, okay. So now we have to deal with the other terms. And so what do we have now? What do we have seen? Here we have an L infinity. In this term we have an L infinity bound. Now we still have to deal with these two terms. And as a consequence, maybe I shorten this up a little bit, how to deal with these two terms. As a consequence, we get the following. We get an estimate for tau. So I put the constant I put in the global constant for tau, modulus of tau times this Fourier transformed Vk tilde at tau square h. We can estimate by a constant. And what do we have in this constant? First of all, here, so this goes into the constant, so this thing here remains. Or let me write it with several constants, C1. Also not. So what do we have here? The Fourier transform of the Vk tilde in the V norm. And then from the additional terms, I just write it down. We get here Fourier transform of the Vk tilde tau in the H norm. And finally, of course, if we where is this? Yeah, of course. So this is something like a constant Fourier transform tau in the V norm. So this is what we get. So now we have to relate this to, or get out of this, we have to get an H gamma estimate, and then from the H gamma estimate by compact embedding, we have to conclude the strong convergence, and with the strong convergence, then we can go in the limit through the equations. So final step, or nearly final step, is now the H gamma estimate. Okay. And what we have to show is, on the level of the Fourier transformed, we have to show that for some gamma bigger than 0, of course, then typically less than 1, we have to show that the fractional derivative is bounded. So in the transformed level, that the Fourier transform of the Vk tilde that would be the function itself, and now the derivative comes in, and this is this power tau to gamma, so this is bounded. So we have to have a bound, an a priori bound. So, okay. The first observation is that this term, which we have to bring in, this 2 tau to the 2 gamma term, this can be controlled up to some constant depending on gamma by a term of the form 1 plus tau over 1 plus tau to the 1 minus 2 pi. I'm not going to prove this now in detail. This is, so to speak, elementary analysis to prove that. I think it's sufficient to see that both terms have the same growth behavior. So we are interested in large tau we can basically ignore these ones here. And then as a power we have here 1 minus 1 plus 2 gamma. So we have the same power as here. So we have two terms which has the same asymptotic behavior, and therefore we can control one by the other with a corresponding constant. Okay. So that means now let's have a look at our integral. That means we can now, up to this constant, we can substitute the power by this corresponding term. Okay, and now we substitute this in two parts. The first part with a factor 1, this we just keep for further consideration. So this first part we keep. Oh, mama. What do we do with the second part? Therefore, we have here we can use what we know already. The second part, now we have something with a tau in front, so we have tau times the Fourier transform of the fk, and this is the term we have dealt with here, so we can plug in this estimate from here, giving plus C0 Fourier transform of fk tilde tau. So, is this correct? No, it's without a square. It's without a square. Okay. So, okay, so what can we do with this? So what we know, I have erased this meanwhile, we have for the fk and the fk tilde, we have an estimate in L2 0 TV. By Parseval's identity, saying that the Fourier transform does not change the L2 norm, this Fourier transform is also in L2 0 TV. This Fourier, yeah, exactly, is also in L2 0 TV. So this term here is bounded in L2 0 TV by the a priori estimate and Parseval's identity. So what do we have here? We have here an integrand which is smaller than 1. Because we always add here something to 1, there's no restriction on the gamma even. We have an integrand smaller than 1. So this integrand does not harm this. So the first term is therefore bounded, because we only have even have here only h and not the v. So the first term is bounded. Okay, let's call this, let's say, A1 plus A2. So A1 is bounded. Bounded always means independent of, and so on. So in terms of an a priori bound. And what about the second term? Second term is a bit more complicated, so let's write this down. So we have here, now we really have to take care of this fractional derivative business. And now we come to a restriction on the gamma times the f vk tilde. Because now we only have here an L1 situation. So now we can estimate this, of course, by Cauchy-Schwarz. Just doing Cauchy-Schwarz, we get here this thing here squared. And we get here this also squared, which we can handle as we have seen. So this term is okay, as we have just dealt with. This term is bounded. So the only thing we have to control is this term. So this integral has to exist. But when does this integral exist? Only if, forget about the 1, only if the power which comes up here is less than 1. So we don't have to run in the situation integral over 1 over tau in the logarithmic situation. So we have to require that, what do we have to have? We have to have 2 minus 4 gamma has to be, 2 minus 4 gamma has to be bigger than 1. And if we relate this to gamma, we have to require that gamma is less to 1/4. So in the extreme case, what we would have in the extreme case, we would have here a 1/2, and we would have here the 1, the non-allowed exponent. So we have to be smaller than that. Okay, so now we are nearly done with the existence proof. Okay, there's still some technicalities to manage, but okay. So now bringing everything together, we have now our fractional estimate for the vk tilde, and because of that, we have that was this compactness theorem 24.2. Because of that, applied with the spaces x equals to v0 equals to h, what we have is we have a compact embedding. Let me write in this form. It's not quite clear, not quite correct formulation of the vk to the L2 0t h. That means we have now in this space, we have strong convergence there. Not only weak convergence by boundedness, we have strong convergence of the Vk to some V in L2 0 TH. So that result was where all the effort was for, to get strong convergence to go through the nonlinear term. There is still some technicality with the boundary conditions, which I now ignore. So actually one has the interval a little bit larger and so on, really to apply that. I ignore this now. So let's do the last step, the limit process. So let's summarize what we have. The one convergence already written down here. And as weak convergence results, we have, as usual, we have the weak convergence in L2 0 TV by the corresponding a priori estimate. And then we also have the a priori estimate in L infinity 0 TH. This is not a reflexive space. And therefore, here we only have weak star convergence. But by the usual distributional comparison argument, all the limits are the same. So we have now a sequence, a subsequence, which converges with these qualities. And now we have to see, can we go to the limit in the equation. So the first step is we have to extend to a general test functions. Up till now, we only had the test functions, the basis functions from the Vk, or the elements from the Vk as test functions. Now we need general test functions, and this we do in the following form. So now we bring the time in, and we select a phi, which is a C1 function in time. So this is only time dependent, a real valued function in time, which vanishes at 0, which only brings in the, which vanishes at capital T, sorry, which only brings the value at 0 in a weak sense, in the trace sense in the equation. So if we now multiply correspondingly with this function, integrate partially in time, then we get the following formulation, and integrate in time the whole thing, of course, and then partially integrate. We get here the Vk. Now here the time derivative is here. So this is the time derivative, and plus the term which comes from the partial integration. One term is vanishing, the other comes, bringing in the initial data. This goes to the right-hand side, and on the left-hand side we still have now, so A is the bilinear form which belongs to the capital A, the linear part of the operator. Now we have the nonlinear part, the tricky part we have to look at. So here the Vk, here the Vk, and here now the test function, Wj phi. And finally the right-hand side, which is this part which comes from the partial integration, taking into account of the initial data V0. So this then leads to a fulfillment of the initial data in the trace sense. That is then, so to speak, the trace formulation times the phi 0 and the right-hand side. So now we have to see what can we do with this. Can we go to the limit? Okay. So that is first. So from The next step is to go from the Wj to a general W from V. This we can also do because just by density. So of course we have any linear combination here also. Those linear combinations are dense, and then we can go to the limit because of the continuity of all the parts which appear here, and here we have shown the continuity in particular of the P. So we can go here to a general function. Now, so what does that mean? So now what about the limit? How is it? Now we first do the, now we do it the other way around. We do first the limit process, and then we go from the Wj to the W. So the limit. Okay, the linear parts are no problem because of the V convergence what we have, so we have to concentrate on the B part. And there the argument is a bit tricky. So what we have to see is so let's have a look at this B part. So we have here these products. So what do we have? We have here derivatives from the VK. We have here components from the VK, and we have the Wj, everything multiplied. And this sum over this triple product has to converge. And the only thing what we know is an L2 convergence, a strong L2 convergence, and correspondingly what we also still know is weak convergence in stronger norms, in an H1 norm. And this we have to use. If we would start only with L2, that would be too much. L2 times L2 times L2, that does not work. So it's a bit tricky here. So maybe I'll only give the steps without going to all the details, because I'm running out of time. I want to finalize this proof. So the first thing is we use by embedding. So H1 to LP, looking at the Sobolev index, we see that this Wj is not only an L2 function, or it's an H1 function. As an H1 function, it's in some higher LP space, and here we can go up to L6 in our, depending on the space dimensions we have here. So the consequence of this is that those products we have to look here, that the Vk times Wj, that they are bounded, and also taking the energy estimates into account, they are bounded in L2 0t, and now not only L2 but LP, so we can go a little bit higher for some P bigger than 2. I skip the details a little bit, but it's important that we can go a little bit higher here. And finally, they are also bounded in L infinity 0t L1. So what do we have here? So now what we now need, which we formulate and in principle also to prove later on, is a new embedding theorem. An embedding theorem which is concerned with those time-space situations. First of all, the pure space-dependent situation. So the embedding of an LP space is quite clear. If I have a triple of indices for LP spaces, we are here in bounded domain, so we know the one with the largest index, with the largest exponent here is the smallest space. and the one with the middle exponent is, so to speak, in between, and this can be also expressed by a multiple cliff interpolation inequality, saying that the middle norm can be estimated by the two extreme norms to certain powers. This is just a consequence of Hölder's inequality. This is a direct consequence of Hölder's inequality. A second step in these interpolation theorems is to bring in here the corresponding powers in the time. And now you see this is a little bit counterwise running. So here we go down from p to 1, but we go up from 2 to infinity. And a consequence of this interpolation lemma, which I have only stated half in some sense, tells us then that we could, so to speak, do that we can we get this estimate, so we preserve the boundedness by going, so to speak, in between. So we go between the 2 and the infinity, and we go between the 1 and the p. As a consequence, we have a bounded in some LP, not LP, let's call it LQ, in some LQ 0t LQ. Of course, we can also write this on the product space for some q bigger than 2. So we have more than L2. That is the important thing. And now with this, we can go through the limit in the B term. I make this a little bit short. So, and the next step is, so we have now this equation. I don't write it down anymore. I would say we have now this equation where we, so to speak, can cancel the k here, but we still have these specific test functions. So the next test functions look at the test functions and go from the Vj to some from the Wj to some W from V in the way I indicated already, and that means then we are done. Then we have the equation fulfilled. We have the equation in distributional sense, and then it goes on. Then with the regularity we have it also in the way we have formulated it. So okay, that's much less than I thought we could have done, but that's the existence proof. And what is still missing, and this we then will do next time. Next time means next Wednesday, not on Thursday. We will do then for the two-dimensional case, we will then do as indicated the uniqueness proof and a little bit on Euler's equations, and we finalize this chapter and then go to the elasticity problems. Okay.